Let's see, just a few announcements. The homework will be coming out, I think, I'm contemplating putting in another or modifying one of the questions, but the homework for next week should be coming out sometime before the homework for this week is due, which is, as you know, tomorrow at midnight. And let's see, what else? Oh, yes, and how many people, may I see a show of hands, who is not yet on a team of at least 2 people? We have 1. Oh, that's not good. 1 person is not on a team. 2, hands high so I can wave them around a little bit. Oh, look, 2 people right next to each other. Okay, you guys can talk to each other, and if you don't match up, let me know. So what's going to happen is I assume that all of you who don't have teams have posted a message on the notice board under group, and that if you do find a team, then take down the message or take yourself off or delete the message or whatever is appropriate to, so that I no longer think that you're looking for a group. And if I still see somebody up there, I'm going to assign you randomly. If I see somebody up there by the end of the week. And I'm hoping, with luck, I might get the project spec out to you at the end of the week, and you can all start working on it. Okay, so administrative questions. Good. Let's get back to what we were doing, which was talking about what these grammar things mean, what this BNF stuff means. So the meaning of a grammar is that it defines a language. And the language is anything that any string of terminal symbols, that is to say, things that the lexer produces, that you can get by a derivation from the start symbol, like this, where each step here, each arrow, is the replacement of one of the non-terminal symbols, either E or S in this case, with the right-hand side of one of those rules. So it's just a sequence of applying the rules, and if you can find a way to get to the terminal string, then you accept that terminal string. So this is a particular example in which I demonstrate that -ID/ID/ID is in fact a string in the language that's described up there. So now in this particular derivation, I always chose to apply a rule to the leftmost non-terminal symbol, which makes this what's called a leftmost derivation. That's just a term. Then, as you might guess, there is also a rightmost derivation, where you apply things always to the right. All right, so that's what this is. That's a fairly simple notion. So, again, I can apply any of the rules for a non-terminal at each point. So I can choose the leftmost in each case, but of course I still have a choice of rules. And it doesn't matter, the surroundings don't matter. I can always choose any of the rules at that point. Hence we call this thing context, and that's where the term context-free comes from. So the interesting thing is that if we agree with ourselves, we make an internal agreement that we're always going to use the same kind of derivation. For example, we're always going to change the leftmost symbol, we're always going to change the rightmost symbol, then I can describe that derivation on the preceding page, on the preceding slide, by simply telling you what are the production numbers that I apply, what's the sequence of production numbers. So here the sequence is something like 1, 6, 2, whatever. Did I get that right in this? Where did I get this 3 business? Oh no, there it is. 3, 1, 6, 2, etc. By just giving you those numbers, and telling you these are the numbers on a leftmost derivation, that's all the information you need to reconstruct what the final string is and what the derivation is. So somehow that sequence of productions is sort of the essence of this of the syntax here, which is kind of an interesting point. Now, another way of representing the derivation of a string is in this familiar tree form. This is called a parse tree. You probably have also noticed that I've used elsewhere the term abstract syntax tree. They're not exactly the same. Parse tree is what you might call a concrete syntax tree because it shows you the entire relationship of the string to the grammar. So here is the same string, and here is a parse tree that corresponds to the derivation that you showed that you saw on the previous slides. Now the way that this works is that each rule, every time I apply a rule, I represent that by writing the left-hand side of the rule as the node, and then recursively I write I write as the children of that node. I write the symbols on the right-hand side of the rule, and then for each of the non-terminal symbols under that, I recursively show how those eventually get derived. So, for example, in the example a couple of slides ago, I took that first E. I took the top E. I changed it to an E/E, and then I changed that first E into an S followed by an ID, and then I changed the S into a minus. And in the derivation tree here, you see that I took the top E here, and I split it into an E, a slash, and an E. And then I took the E, I split it into an S and an ID. The first S, this should have gone to a minus. For some reason that got left off. The first S goes to a minus, and then the second goes to, and then the ID is already a terminal symbol. Okay, so given this particular string, well, actually, this is a new string. This is a string without any minuses. So all of the S's in this particular string go to nothing. So my question here is, what would be a rightmost derivation for this same string? So we've seen a leftmost derivation for a somewhat different string. What would be a rightmost derivation for this string? So remember, rightmost derivation, I give you a sequence of sentential forms, except that instead of what we did here, where every time I change the non-terminal that I change each time is the leftmost, I want you to give me another derivation, a derivation for this string, in which the symbol that you change is the rightmost one. What would you do? Any takers? The first step, hint, classroom participation hint for impressing the instructor. Look for the easy cases and jump on them. Makes you look very impressive. Yes, impress me. Yes, there you go. You see, that's how easy that is. I mean, there's no choice. You have a single symbol, so you've got to change E to E/E. It's the same as before. Okay, what would the next step be? Yeah. So what would that be? So that E would then turn into what? Uh-huh. Yeah? Right. So S right, left paren, E paren. And what would the next one after that be? Yeah. Okay, right. So the rightmost E would then be, which would be, let's point at the screen, so which would then be this guy, goes to E/E, and so forth. So let's see, do I have the, yes I do. So, and eventually, and so the entire sequence looks like this blue thing at the bottom, and eventually gives us the derivation. Now you notice that there's also a leftmost derivation for this same string. It looks kind of like the first one we did, but except that the S's come out differently. But the interesting thing here is that there are two different derivations, but in each case we get exactly the same tree. So this is to sort of illustrate the relationships between derivations and parse trees. Now, the interesting thing here is that this particular grammar has a funny characteristic. So let's go back and look at this guy. Is there another parse tree? Question. Is there another parse tree that produces the same, that starts at E at the top and has this, stop pointing at the screen. It has the E at the top and has this thing at the bottom, but has, you'll have to match and slash only matches that first, that one E/E thing. You're basically going to have to somehow match the second E, the rightmost E, to this whole thing. You don't have any choice. And you're going to have to match the first E to this thing. You don't have any choice. So you're actually constrained. And in this particular case, there is in fact only one tree that matches this particular, there's only one tree that matches this particular string. And when there is only one tree, for every tree, there is a single leftmost derivation or rightmost derivation. So basically everything here is unambiguous, and there's no possible question about what kind of derivation you've got, or what kind of what rules you apply. But for this problem, for this one here, ID/ID/ID, I claim that there are actually two parse trees, either of which produces ID/ID/ID. So what would those be? I think there are two parse trees whereby I can match that thing to E. Yeah.
Is it in one case you make the first ID/ID expression?
G for L of G is ambiguous. The fact that it doesn't matter that there are some strings that have just one that are unambiguous, that's irrelevant. The grammar is ambiguous because there is more than one match to this, one way of matching this string. Now, why is that important? That wasn't important in regular expressions. When we were doing regular expressions, it wasn't important because when we were doing the lexeme stuff, we really weren't, I mean, some of the homework problems which dealt with Python regular expressions or Java regular expressions or what have you, you were interested in looking at pieces of the match. But in general, when we're matching things with regular expressions, the sort of classically, you're not interested in how the thing matches, you're just interested in whether it matches. But now that we're doing parsing, the structure here, the structure of these parse trees is now of interest because, as we'll see, it corresponds to how you group these symbols. Now slash, I carefully chose slash because slash, as you know, is not associative. If I evaluate x divided by y divided by z, and I group it as x divided by y, the quantity divided by z, that gives me an entirely different answer from x divided by the quantity y divided by z. So, as it will turn out, the structure of the parse tree is used, the whole great power of this parsing stuff and BNF in general is that you can use the structure of the grammar to drive the translation. So it becomes important how this thing gets matched. If you look at the lecture index, the thing here is what we're looking for is again is whether this thing, what the particular structure is. So what we're going to do is we're going to, just as we did in the lexical case, where you associate with each, where in doing say a lexer, a tokenizer, you associate, you tell for each regular expression that describes a token, you say what kind of token is this. We're going to do the same thing here. We're going to attach, every production is going to have a rule, a translation rule attached to it, so that every time a particular construct appears in your language, that will trigger a particular the translation of that construct. Now in Bison, I'll start with Bison, is some function of the translations of the first and third elements on the right-hand side. So the translation of the whole thing, the translation of E/E, is a function called do divide of the translations of the first E and the translation of the second E. So that means, so this looks familiar. I mean, this is the kind of thing that we sort of pound into you in CS61A and 61B, a recursive tree walk. You're going to, in effect, what you're going to do is you're going to do a bottom-up tree walk of this parse tree, in effect, except you'll actually be doing it as you're constructing it. And as you come up from the bottom, you'll be constructing these semantic values of each object and putting them together, synthesizing them into the semantic value of the whole thing. Now, we actually get this the way that the Bison system, or the extension that we'll be using, does this is by doing a rightmost derivation, but doing it in reverse. So working from the bottom up, since the last step in a derivation is the thing that produces the leaves at the bottom, some leaves at the bottom of the tree, the terminal nodes at the bottom of the tree. If we do it all in reverse, sort of go from the terminal string back down to E, then what we'll be doing is in fact traversing that parse tree in a bottom-up tree walk, so post-order tree walk in effect, and that's what you do. It's actually pretty neat. So let's take a look at a specific example of a construct, the conditional statement. So in Python there is this if then else construct, and it has the structure that one of the sort of usual way that you do it is that the syntax for other expressions, and for other statements is handled elsewhere. We won't worry about that, and we'll just look at this. So here we go. So an expression will be some stuff, don't know what, doesn't matter, handled elsewhere. A statement will be a whole bunch of things, including a conditional statement. So cond is a kind of statement. And so the conditional statement looks like this. It's going to be an if followed by some sort of an expression, followed by a colon, and then something that the Python people, for reasons of their own, call a suite. I don't know why, but there it is. It must be some European language or something that makes sense. I'm not sure. In French, it means what? Following or something. And then elifs are the else-if clauses, and then finally an else clause, if any. So one of these suites is simply an indented section of text, which means it's an indent followed by some statements followed by a dedent. And now we get this standard idiom that you see all over the place with BNF, which is that to represent a sequence of statements, of one or more statements, we use this kind of production. It's either a statement or a bunch of statements followed by a statement. The recursive list definition, meaning one or more. And the elifs are elifs can either be empty, there don't have to be any, or you can have an elif and then another looks like an if. And else is, again, either empty or it's else expr. That's wrong. There shouldn't be an expr here. Shame on me. It should be just else : suite at that point. Okay, so this is the kind of syntax that you want, and it's pretty straightforward, with the exception of that one mistake. I wonder how that mistake has lasted all these years. Because people are sleeping. That's why it is. I wasn't taken to task. You should be taking me to task. It was a test. It was intentional mistake. Consider this a warning. All right, so next. Yes. Shouldn't, pardon me?
In the statements,
Uh-huh.
shouldn't it be statements as opposed to statement, in order to be regular?
Well, this isn't regular. In fact, already this thing is, okay, so the question is, I could also have written this as statements get statement or statement followed by statements. That also works. And if we were doing this, if we wanted a regular language, you'd do that. But in fact, this grammar already is not regular. There's something about this that makes it irregular, right? And that is that suite there, which is in the middle of this thing, contains a statement, and a statement can be a con. So you can actually invoke con in the middle of it, and the thing is no longer becomes regular. And we'll see. We'll pursue that a bit later. But in this particular example, BNF is strictly more powerful in its descriptive ability than the regular expressions that we've been dealing with. Now, Java, on the other hand, presents a rather an interesting case. So this is just plain if then else or if else. So here we go. This looks pretty straightforward. It looks the same as before. We have the cond is in parentheses. We have if something or other statement and else, and the else clause is either empty or it has an else clause in it. End of story. Looks really simple. But it doesn't work exactly. And that's because of this example right here. This is an example of what's called the dangling else problem. In which if I have if foo, if bar, if foo, then if bar, then walk, else chew gum, it's ambiguous from the grammar that I've written whether the then part of this guy is the whole thing. Maybe I should remember to do this. So it's ambiguous whether this whole thing is the else part, or whether this else here applies to this if. So does this else apply to this if, or does it apply to that if? Question, why doesn't Python have this problem? Python doesn't have this problem. Java has this problem. C has this problem. But not, or rather, writing a grammar for Java has this problem. Writing a grammar for C has this problem. But writing a grammar for Python does not have this problem, nor does writing a grammar for Bash, for the Bash script language, doesn't have this problem either. What's the difference? Why isn't there a problem? Yeah. Right. So we don't. So we require that the thing be bracketed. So that means actually the problem doesn't occur in Perl either. Perl, for example, requires that all these things be bracketed. So this is back in days when I was actually a young man, they had these arguments about should you fully bracketed constructs versus non-bracketed constructs. Now we have firmly resolved not to resolve that problem and moved on, as so often happens, and left the problem to later generations, much as we're leaving the national debt to later generations. Okay. So those are a couple of, and then we can resolve this problem but we can resolve this problem in a number of ways, and the one way to do this is to introduce two different kinds of statements that you can put after if and else, which is either a closed statement, that is one that's fully bracketed if then else, and an open statement. And by doing this, you basically force the thing after the if. If there's going to be an else, you force the thing after the if to be completely bracketed. So if there's an else after the if, then anything between the expr and the else has to be completely bracketed, which relieves the ambiguity because it means that you have to have an else clause for any if that follows the then. So that's fine. Of course, you look at this thing and it looks totally opaque to you. I mean, why does this work? Why does this prevent the dangling else problem? And you'll have to puzzle over it. I mean, basically, I can say to you, well, the dangling interpretation doesn't. One interpretation doesn't work with this, but it's not. But I have to say, it's not at all clear what you can do about that. Okay, why don't we take a break here? We're probably going to delay the next part by another day, but since people at least some people have complained that the course is going too quickly, that's probably a good thing, so I'm not going to worry about that. All right, let's take a break.
Just kind of curious about the pace. I mean, it seems actually not fast at all. I'm wondering, is it going to stay this way, or are we going to get hit with it after week 5?
Oh, you mean am I? Well, the pace, it does vary, I admit, but I want to. It's kind of important that the basics sink in, because the next topic is this very esoteric details of how this is actually done behind the scenes, which is rather involved. And if you miss this, I mean, this is really, in some sense, from a practical point of view, this stuff is the important stuff. And the rest is just stuff that I throw in because I'm mean, and because I've done it for years. But so it's important that we get this. and we'll actually go over the more technical stuff much faster than you'll be able to absorb it. So that'll much faster than you will be able to absorb it. So
Which stuff are you talking about?
how parsers work.
How they work?
Yeah.
Is there a particular chapter or something I should be reading to?
It's in the notes. It's in the notes. Yep. Yeah.
On the statement, it has ... vertical bar on ...
Uh-huh.
Does that mean ... or con or ...
No, it means that there are other kinds of, it's ellipsis. There are other kinds of statements that we're not showing you here. And
why isn't it just ... vertical bar?
Yeah, I could do that. It doesn't matter. If you were looking at an actual grammar, the if statement would probably be in the middle somewhere. It wouldn't be on the end. So I just put dots on both ends to be safe, Yeah.
I just joined this class yesterday.
You'll have to get an account form. All right. Well, you'll have to come with me to my office to get it after the class.
Okay.
All right, let's get started again. So I said a moment ago that people were saying the class is going too fast, and now I just got a comment that said the class is going too slowly. Would you guys please go out and duke it out there, decide which way it is, and let me know how you resolve it, and we'll adjust the class speed accordingly. Okay, so here's a little puzzle. I want a grammar that accepts the same strings as this non-deterministic automaton. So I'm looking for the. This should be pretty easy. I'm looking for the grammar that gives me this. First of all, what is the describe to me? What is this language that we've got here? We've seen this before, actually. Mumble, 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 mumble. Yes.
A language of zeros and ones.
Right, is divisible by 2 or 3. Okay, good. So how do we write that in BNF? Any takers? You can give me either a rule for the start symbol, or you can give me a rule for something that goes inside someplace. Yeah.
Start goes to even ones or multiple 3 ones.
Okay, good. Okay, so we can represent this thing here just as we would with an NFA. We can represent it with an OR. So that means that all we have to do is now define 2 symbols, even ones and what was the other 3, 1, 3, or 3 ones or something like that. So even or divisible by 3. There is no word for divisible by 3, is it? Is there? Even, maybe threeven or something. I don't know. Okay. Okay, so I'll take any comers. Who would like to tackle, say, even ones? Yeah.
So if you look, so let's say that we define evens as 1 even, or 1 even 1, or even 1 1.
1 even. Oh, I see. Evens as okay, yeah, that's certainly one way to do it. So what? So that's But what happened to 0? Somehow 0 got left out of that.
We can add in zeros on the other side of the 1, so we could have 3 positions.
Uh-huh.
And one of those would be 1, the other 2 would be 0.
Okay. All right, so you're saying a 1 followed by a bunch of zeros, followed by a 1, followed by a bunch of zeros, followed by a 1, followed by a bunch of zeros. Something like that. Okay. Almost. Just one more step. Yes.
You start by defining like a zeros symbol, for example, match their 1 or 0.
Okay, that's a good idea. So we'd certainly want to throw that into the mix. So now we can use that wherever we want to say bunch of zeros.
And then the 1 divided by 3.
Oh, wait, we're not finished with the divisible by 2, actually. We're almost there. There was just one little piece missing. Yes. Uh-huh. Uh-huh. Okay, right. We have to be able to have more than one group of 2 ones. So you have to have you basically have to repeat that pattern any number of times. And we get we get the same thing for the odds as well. So it can be something like this. I don't know why I chose those particular names. I probably could have done better. So this is one way to do it. And this is, this is a different way of doing it. I should probably write up your way as well. But in this case, we can have either 1 or 4. And the idea here is that S1, S2, and S3 correspond to the state of having one or two ones modulo 2. So whether you have an even number of ones so far or an odd number of ones so far, that's basically what it corresponds to. So I can go from so in this case, if I have an even number, so to give me an even number of ones, I can either have 0 followed a whole bunch of zeros followed by S1, or I can have a 1 followed by, or I can have a 1 and then go to state S3, which basically stays in S3 until I find. Oh, this is Wednesday, isn't it? Yes, Fast Wednesday. Okay, so we'll come back. We'll end up with this example next time, and come on.